Moment equals force times perpendicular distance, and the units are Newton meters. Moment is the turning effect about a point. You need to remember that the weight of a uniform beam acts at its centre, the centre of mass. In equilibrium means that the total moments will be zero. In other words, it won't be turning because the turning forces are balanced. An ornament of mass 600 grams sits 10 centimetres away from the wall on a floating shelf fixed at point A. Find the moment at A. The moment at A, and that's going to equal the force, which is due to its weight, so that's 0.6 g, times by the perpendicular distance it is from A, which is 10 centimetres, but we need that in metres, so that's 0.1. So that is 0.06 g, and if we evaluate that, we find that is 0.588 Newton meters. In this second example, we have a beam resting on 2 points at A and B, and we have a child standing at Q at that end who has a mass of 15 grams, and we need to find the two reactions, R1 and R2. So we're going to find R2 first of all, and we're going to do that by taking moments about point A. We're choosing to do that because we don't know R1, and by taking moments about A, that means we don't need to know about R1 in order to carry on. So let's have a look at what forces we've got. So we've got R2, and how far away is that from A? So we've got 20 centimetres between P and A and 40 centimetres between B and Q. That's 60 centimetres. So the distance between A and B must be 140 or 1.4 metres because we need it in metres. R2 is going to be times 1.4. So the other force that we've got, because of the weight of the child, and we were told the weight of the child was 15 kilograms, so that'll be a 15g force acting there at Q right at the end. Even though I haven't quite drawn it as showing right at the end, we're going to treat it as if that is. But notice that that force is in the opposite direction, so that's going to be minus 15g times by, so that's 1.4 plus the 40 centimetres away from A, so that's 1.8. Also need to take account of the weight of the beam itself, which we can see is 20 kilograms, so it's got a force of 20g, and again that's acting against the R2 force, so that's going to be minus 20g, and that's in the middle. And we're told the whole thing is 2 metres, so that's 1 metre from P. So if we take off the 20 centimetres, we can see that that's going to be times by 0.8. All of those have to equal 0 because at this point in time the beam is not rotating or tipping at any point. This leads us to 1.4 R2 being equal to 1.8 times 15g plus 16g. So R2, when we work that out and divide through by 1.4, comes out as being 301 newtons. Now we're going to take moments about the point P so that we can work out what R1 is. So first of all, R1 itself, R1 is 20 centimetres away, so that's times by 0.2. We then have the weight acting on there, which is acting in the opposite direction. So that's minus 20g, and that's times by 1 this time. And we have the weight of the child again acting against, so that's minus 15g, and that's 2 meters away, so that's times by 2. Also we have R2 acting in the same direction as R1, so that's a plus R2. And how far away is that? That is 1.6 away, and that equals 0. So if we tidy this up, we'll have 0.2 R1 equals 20g plus 30g, so that's 50g, minus 1.6 times R2, which we know is 301. And then if we take that and divide everything through by 0.2 as well, we'll end up with R1 equals 42 newtons. Here we have the same setup but a different question. So we're being asked to find the maximum weight of the child before the beam tips over. Now, if we know that the beam is on the point of tipping over, that means that all the force, all the stress is going to be on point B and not point A. And what that will tell us, therefore, is that R1 will be 0 at that point in time. We're going to do this by taking moments about B. What forces do we have? We have the weight, the 20g. That's a metre away from Q, so that means it's 0.6 away from B. And then acting against that, we have the weight of the child that we don't know, so that's minus mg, and that's 40 centimetres away, so that's 0.4. And those need to balance. So what we get out of this is that 0.4 mg needs to equal 12g. So our mass will be 12g over 0.4g. So you can see the g's are just going to cancel. 4's into 12 would be 3. So this is going to be 10 times bigger than that. So that's going to be 30 kilograms. In this diagram, there's a uniform rod of 1.5 meters in length that's being held in equilibrium horizontally by 2 wires, and they want us to find the tension in those 2 wires, T1 and T2. So the first thing we need to do here is take moment about point C, and we're going to try and find T1. Now we need, remember, the perpendicular distance, and therefore we need the perpendicular force. So we need the component of T1 that's doing this. It's opposite the angle, so that's going to be T1 sine 45 degrees. T1 is acting at B, so that's 45 plus 15 centimetres, so that's 60 centimetres, so times by 0.6. And then we've got the weight of the beam, so that's acting in the opposite direction. That is 15 centimetres away from C, so 0.15. That equals 0 because everything's in equilibrium. So T1 will equal 0.3g divided by 0.6 times sine of 45 degrees, which is 1 over root 2. And so when we work all of that out, we get 6.9 newtons. Now we're going to take moments about B so that we can find T2 this time. So we're going to need the perpendicular vertical component of T2. So that's T2 sine 30 degrees. And how far away from B is that? That's also 60 centimetres away, so that's 0.6. Then we've got the weight again acting in the opposite direction, but this time it's times by 0.45 because it's 45 centimetres away. That's all balanced, and so that leads to T2 equals 0.9 G, and remember sine 30 is a half, so that's going to be divided by 0.3, and we work that one out. That gives us 3G, which is 29.4 newtons.